The universe should not exist. Every single atom in your body, every star in the sky, every galaxy spinning through the cosmic void should have been obliterated the instant they came into being. Yet here we are, contemplating this impossible reality. The reason for this cosmic paradox lies in one of the most mysterious and destructive substances known to science, antimatter. And the story of how our universe survived its own annihilation reads like the greatest thriller ever written, with stakes that couldn't be higher and a twist ending that scientists are still trying to understand. Picture this: 13.8 billion years ago, in the first trillionth of a second after the Big Bang, the universe was nothing but pure energy. Then something extraordinary happened. This energy began transforming into matter, but according to every law of physics we understand, it should have created equal amounts of matter and antimatter. When these two substances meet, they don't just react or combine like ordinary chemicals. They completely annihilate each other, releasing pure energy and leaving absolutely nothing behind. So here's the mind-bending question that keeps physicists awake at night. If the Big Bang created equal amounts of matter and antimatter, and these substances destroy each other on contact, how is there anything left in the universe at all? Why aren't we sitting in an empty void of pure energy? The answer to this question takes us on a journey through the most extreme physics imaginable, involving temperatures that would make the center of the sun seem like an ice cube and densities that defy human comprehension. Let me take you back to those first moments after the Big Bang, when the universe was smaller than a single proton, but contained all the energy that would eventually become every galaxy we observe today. At this point, temperatures reached an incomprehensible 100 billion degrees Celsius. In this cosmic furnace, energy was constantly converting into particles and antiparticles through a process that seems almost magical to our everyday experience. When I say antiparticles, I'm talking about the evil twins of ordinary matter. For every proton, there exists an antiproton with the exact same mass, but opposite electrical charge. For every electron spinning around an atom, there exists a positron that's identical in every way, except its charge is positive instead of negative. These aren't theoretical constructs dreamed up by physicists. We've created antimatter in laboratories, stored it in magnetic fields, and studied its properties extensively. The creation process in the early universe worked like this. Pure energy would spontaneously convert into particle pairs, always creating one matter particle and one antimatter particle simultaneously. This isn't speculation. We observe this happening in particle accelerators today when we smash protons together at incredible speeds. The energy from the collision creates new particles, but they always come in perfectly matched pairs of matter and antimatter. Now here's where the story takes its first dramatic turn. If the universe had created exactly equal amounts of matter and antimatter, these substances would have found each other almost immediately in that incredibly dense primordial soup. When a proton meets an antiproton, both particles vanish completely, converting back into pure energy in the form of gamma rays. The same fate awaits electrons and positrons, neutrons and antineutrons, and every other particle-antiparticle pair you can imagine. The mathematics of this annihilation process are beautifully precise and terrifyingly complete. Einstein's famous equation, energy equals mass times the speed of light squared, governs this transformation. When matter and antimatter annihilate, 100% of their mass converts directly into energy. This makes antimatter the most efficient energy source theoretically possible. If we could somehow harness this process, a single gram of antimatter reacting with a single gram of matter would release the energy equivalent of several nuclear bombs. But in the early universe, this efficiency would have spelled disaster. Within the first few seconds after the Big Bang, every particle should have found its corresponding antiparticle and disappeared in a flash of gamma radiation. The universe should have ended up as nothing but a sea of photons, forever expanding and cooling, but completely devoid of the matter needed to form stars, planets, and eventually, life itself. Yet obviously, this complete annihilation didn't happen. Look around you. Every atom in your body is proof that somehow, someway, matter won the cosmic battle against antimatter. Scientists estimate that today's universe contains virtually no antimatter at all. The few antiparticles we detect come from cosmic ray collisions or radioactive decay, not from primordial antimatter that survived since the Big Bang. This leads us to one of the most profound mysteries in all of science, the matter-antimatter asymmetry problem. Somewhere in those first moments after the Big Bang, the universe developed a preference for matter over antimatter. But this preference was incredibly slight. Scientists believe that for every billion antiparticles created in the early universe, there were approximately 1,000,000,001 matter particles. That tiny imbalance of 1 part in a billion saved everything. When the Great Annihilation occurred, nearly all the matter and antimatter destroyed each other, but that minuscule excess of matter particles survived. These leftover particles became the building blocks of every atom in the observable universe. Your body, composed of roughly 7 octillion atoms, exists because of an imbalance so small it's almost incomprehensible. But this raises an even deeper question. What caused this asymmetry in the first place? According to our current understanding of physics, the laws governing particle creation should be perfectly symmetric. If energy converts to matter and antimatter in equal amounts, and if the fundamental forces treat particles and antiparticles identically, then how did the universe develop its preference for matter? The answer lies in a phenomenon called charge parity violation, one of the most subtle and important discoveries in particle physics. In the 1960s, scientists discovered that certain fundamental processes don't treat matter and antimatter with perfect symmetry. The differences are incredibly small, often measured in parts per thousand or even smaller, but they're real and measurable. These violations occur through the weak nuclear force, one of the 4 fundamental forces of nature. Unlike the electromagnetic force or gravity, which treat particles and antiparticles identically, the weak force shows a slight bias toward matter over antimatter. This bias manifests in the way certain particles decay, creating slightly more matter particles than antimatter particles in the products of these decay processes. In the scorching heat of the early universe, when temperatures exceeded 10 trillion degrees Celsius, particles were being created and destroyed at rates that dwarf anything we can produce in laboratories today. During this cosmic chaos, the subtle asymmetries in the weak force gradually tilted the balance in favor of matter. Each interaction that violated charge parity symmetry nudged the universe a little further away from perfect balance. The process was like a cosmic coin flip, where the coin was weighted ever so slightly toward matter. Individual flips might still land on either side, but over trillions upon trillions of interactions, the bias gradually accumulated. By the time the universe had cooled enough for stable particles to form, matter had achieved its slight but decisive victory. This period of cosmic evolution, known as Baryogenesis, occurred when the universe was less than 1 second old. During this time, the fundamental particles that would eventually form protons and neutrons were still in a state of flux, constantly changing identities through interactions mediated by the weak force. The specific mechanisms of baryogenesis involve some of the most advanced physics known to science, including theories about the Higgs field and speculative particles called leptoquarks. But the antimatter story doesn't end with the early universe. The implications of matter-antimatter physics continue to shape our understanding of the cosmos today. For instance, scientists are still searching for regions of space where antimatter might have survived in significant quantities. If such regions exist, they would be observable through the characteristic gamma radiation produced when antimatter from these regions encounters the matter that pervades most of the universe. So far, these searches have come up empty. Observations from space-based gamma-ray telescopes show no evidence of large-scale matter-antimatter annihilation anywhere in the observable universe. This suggests that the matter victory was universal, not just a local phenomenon in our particular region of space. The entire observable universe appears to be made almost entirely of matter, with antimatter relegated to trace amounts created by high-energy processes. The study of antimatter has also opened up incredible technological possibilities that sound like pure science fiction. Scientists have successfully created and stored antimatter atoms in laboratory conditions, using powerful magnetic fields to prevent the antiparticles from touching the walls of their containers. These experiments require some of the most advanced technology ever developed, including magnetic fields thousands of times stronger than Earth's magnetic field and vacuum conditions better than those found in deep space. Creating antimatter is currently one of the most expensive processes known to humanity. It takes enormous amounts of energy to produce even a few atoms of antimatter, and storing it requires constant power to maintain the magnetic containment fields. Current estimates suggest that producing a single gram of antimatter would cost more than the entire gross domestic product of Earth. But the potential applications continue to drive research forward. Theoretical antimatter engines could provide propulsion systems for interstellar travel that make current chemical rockets look like Stone Age technology. Since matter-antimatter annihilation converts mass to energy with 100% efficiency, antimatter rockets could theoretically accelerate spacecraft to significant fractions of the speed of light. Such propulsion systems could reduce travel times to nearby stars from tens of thousands of years to decades or even years. Medical applications of antimatter also show tremendous promise. Positron emission tomography, already used in hospitals worldwide, relies on the annihilation radiation from positrons to create detailed images of internal organs. Researchers are exploring more advanced antimatter-based medical treatments that could deliver precisely targeted radiation therapy with minimal damage to healthy tissue. But perhaps the most profound implications of antimatter research relate to our understanding of the universe itself. The matter-antimatter asymmetry that allowed our existence represents one of the greatest unsolved problems in physics. While we know that charge parity violation occurs, we don't fully understand why it happens, or whether current theories adequately explain the magnitude of the asymmetry observed in the universe. Some scientists believe that discovering the complete explanation for matter-antimatter asymmetry could revolutionize our understanding of physics as fundamentally as Einstein's relativity or quantum mechanics did in the 20th century. The answer might lie in dimensions beyond the three spatial dimensions we experience, or in subtle properties of the Higgs field that gives particles their mass, or in completely unknown physics that operated during the first moments after the Big Bang. Current experiments at the Large Hadron Collider and other particle accelerators continue probing the boundaries between matter and antimatter physics. Scientists are studying the properties of antimatter with unprecedented precision, looking for any additional asymmetries that might explain why the universe developed its preference for matter. These experiments require detecting differences so small they're at the very limits of what our most sensitive instruments can measure. The cosmic microwave background radiation, the afterglow of the Big Bang still visible throughout the universe, provides another window into the matter-antimatter story. The patterns of temperature fluctuations in this radiation carry information about the conditions in the early universe, including the processes that led to the dominance of matter over antimatter. Future space missions will map these patterns with even greater precision, potentially revealing new clues about the cosmic asymmetry. As we look to the future, the antimatter story continues evolving. Theoretical physicists are developing new models that might explain the matter-antimatter asymmetry through connections to dark matter, the mysterious substance that makes up most of the mass in the universe, but doesn't interact electromagnetically with ordinary matter. Some theories suggest that the same processes that created the matter-antimatter asymmetry might have also created the dark matter that shapes the large-scale structure of the cosmos. The story of antimatter and the early universe ultimately reflects the incredible improbability of our own existence. The fact that you're watching this video, that Earth orbits the sun, that stars shine in the night sky. All depends on a cosmic coincidence, so unlikely it seems almost miraculous. A tiny asymmetry in the fundamental laws of physics, operating over an incomprehensibly brief moment in the first second after the Big Bang, made all the difference between a universe filled with stars and galaxies and one containing nothing but empty radiation. This realization should fill us with wonder at the delicate balance of forces that made complexity and life possible. The antimatter story reminds us that the universe we inhabit is far stranger and more remarkable than our everyday experience suggests. Behind the familiar world of atoms and molecules lies a cosmic history of unimaginable violence and beauty, where the very survival of matter itself hung in the balance during moments when the universe was younger than a human heartbeat. The next time you look up at the stars, remember that every photon of starlight reaching your eyes carries the legacy of that ancient battle between matter and antimatter. The light itself exists because matter won that cosmic war by the narrowest of margins. And in that victory lies perhaps the greatest story ever told: how the universe survived its own birth and gave rise to the incredible complexity and beauty we observe today. The antimatter mystery continues driving scientific discovery, promising new revelations about the deepest workings of reality itself.